Okay, I am going to give you guys a lesson on mass spectroscopy. And the first thing that I want you guys to know is common fragments that we expect to see over and over again when we do mass spectroscopy. Numbers that it's handy if you memorize them, because it'll make things go quicker on an exam or test. A methyl group is 15, ethyl group is 29, a propyl group is 43, a butyl group is 57, and an aromatic ring is 77. And these are a couple of the most common fragments that we're going to see when we do mass spectroscopy. If we start by looking at ketones, we'll take pentanone, and this is 3-pentanone, okay? It has a molecular mass of 86, and that would generate an M plus peak, which is consistent with the molecular weight of 86. And we see that in the spectrum. So we validate that the mass is actually 86. And then we also find the largest peak within the spectrum, and we call that our base peak. And this base peak actually is at 57. So this base peak is at 57, and that would be consistent with this fragment. And of course, this would be 29 for our ethyl. Okay? And so what we typically expect to see on all of our mass specs is that base peak is going to be probably the major fragment that we expect to see. And 57 is the major fragment because we can clip off that 29, which shows up here. And that would be the result of clipping an ethyl there. But you could also clip to the other side of the carbonyl, but that would result in the same two fragments. So that would just be redundant. So the major peaks are then 29 and 57, and that's consistent with what we would expect to see for 3-pentanone. The next structure that we want to look at is 2-pentanone. And so we could use our knowledge and understanding of fragmenting patterns to now distinguish between the two ketones. If you were given both of these ketones with a mass of 86, you would, and you were given a spectrum, you could choose between the two based on the fragments that we see. When we have 2-pentanone, the preferred place to fragment would be here. And that would clip off a propyl group, which has a mass of 43, and that is our base peak. And the acetyl group is 43 as well. And so we see that as the major, almost exclusive peak is 43 and 43. And that would allow us to distinguish between those two ketones just by examining the two mass specs and noting the different ways that they would fragment. We can go on to another example, and I chose this example because there's two pathways in which you can split. And we obviously can split off the isopropyl and then have this carbonyl, or you could potentially have split off, you could have split off an ethyl group and had the other possibility. Well, it turns out that the preferred fragmentation pattern would go in this direction, which would generate a secondary radical versus a primary radical, even though we probably see some of this fragmentation because we do have a mass, a peak at 29. However, the major peak at 57 is consistent with this pathway, 43 and 57. Now, if we look at alcohols, alcohols like to fragment very much the same way that we see with carbonyls. They want to fragment alpha to the OH bond. And in this case, the both possible fragments would result in exactly the same two ions at 29 and 59, and lo and behold, our base peak is at 59, and we see our molecular weight or molecular ion peak at 88. If we presented ourselves a choice of, say, this particular compound, there's an A and B pathway, and the A will give us a different fragment than the B pathway. The A pathway would give us an isopropyl at 43 and the alcohol of 59. If we did the B pathway, we would get a 73 and a 29. And you notice our base peak is at 59. So A is the major fragmentation pathway for this particular alcohol. We can also look at esters. And again, what we see when we look at esters is an AB possibility for fragmenting. And you may see sometimes one or both fragmenting patterns present, but we certainly expect to see our base peak reflected in one of the fragmentation patterns. So if we cleave on each side of our carbonyl, we have one pathway that'll give us 31 and 57 for fragments. And if we cleave on the B side, we would get 59 and 29. Well, we look at our base peak, and our base peak is at 57. And that's consistent. However, we must have also had some B cleavage as well, because we see the 29 represented by the ethyl group that's present here. So both pathways are occurring, but we can certainly say that this fragmentation is the predominant fragmentation taking place in that molecule. When we go to the next ester, we again have an AB pattern for fragmenting. And there's, we look at the B pathway and look at the fragments, 59 and 73. We look at the A fragmenting pattern, and that's 71 and 31. Our base is actually 43. So we expect B pathway to be the predominant pathway. However, we also see a major peak at 71, which is indicative of the B cleavage taking place the A cleavage taking place as well. So sometimes we see both possible ways of fragmenting. Now moving on, the last area that I wish to talk about for you today happens to be aromatics and halogens. Aromatics and halogens. And so whenever we see any kind of aromatic compound, if it's substituted with one substituent, you'll often see simple bond cleavage, and you will see the benzene cation, which is at 77, and we see that, okay? But what's interesting here is that chlorine has two isotopes, chlorine 35 and chlorine 37. And their relative abundance happens to be that chlorine 37 is about one-third the presence of chlorine 35. And that'll be reflected in the mass peak. So if chlorine 35 is the predominant isotope, we'll have a molecular ion peak, an M+ peak, and then following behind it, we will see an M+2 peak that's due to the chlorine 37, which is typically one-third the size, or always one-third the size of the M+ peak. And so we look for this pattern. If you think you have a chlorine present, you will always see in your spectrum a molecular ion peak and an M+2, the isotope that follows. One other small thing to take note of here, and we don't always see this, but in this case, you're looking at these additional little peaks at M+1 and then M+2 plus 1. And these little tiny peaks that appear sometimes next to our molecular ions, they are due to the presence of carbon-13. And we don't typically worry about them, but just for the sake of educating you, the very small peaks are associated with carbon-13. And that's what we see for chlorine. And if we look at the other aromatic halide, bromobenzene, bromine has two isotopes, bromine 79 and bromine 81. And when we see the fragmentation, obviously we see the 77 for the aromatic ring. And then when we look at the total mass of 157, we get the 157, which is due to the bromine 79 isotope. And then we see 2 units further to the right, we see the M+2 peak, which is due to the bromine 81. Bromine 81 is 98% of the size of the bromine 78. So if we called bromine 78 as 100%, bromine 81 would be 98. So you'll see a pair of molecular ion peaks that are almost exactly the same size, that are exactly 2 units apart, and that would be indicative of a bromine type compound. And it's easily observed when you take a mass spectrum. All right, that will do it for my lecture on mass spec. I sent these structures to you, and I would like for you to go to those structures and look at them and review them and make sure that you are very well versed in mass spec. I will be in touch again.